now you can hear me. My talk is not necessarily going to be very, very technical, but more of an overview of what I did during my PhD project in general. And our domain was how to make confidential tabular data more findable, accessible, interoperable, and reusable. And I'm going to show some approaches that we've proposed, which are based on metadata, on how to, sort of facilitate. Yeah.
One technical interruption. I think you still need to share your screen.
I need to share my screen.
Yeah.
So now you can see it. Okay. So firstly, I'm going to briefly state what the problem is. Then I'm going to define what metadata is, even though some of you might already know, and the concept of dataless tables. And then we're going to look at how we can generate this metadata, enrich it, and eventually some ways we can reuse it and actually do something with it. So firstly, confidential data, it's also data that cannot necessarily be seen. It might have privacy sensitive information inside. It can be medical records, population statistics, but these also apply to any other type of copyrighted data that people just don't want to have open and freely on the web. And it's not only difficult to access, but it's also very difficult to discover because the data owners tend not to put information about even the existence of this data online. So people know that in theory it's supposed to be there, but we can't actually know who has it, where it is, how to get it. There has been some, in a way, solutions to overcome the problem of confidential data, such as aggregated statistics, the personal health strain, which I don't know if you know what it is, and the secure computers. But they do offer limited help in a way. Aggregated statistics, obviously, if you want to do something on the individual level, they're a bit useless. Personal health strain and secure computers work similar in a way that the researcher does not get access to the data, but they go to either on the cloud or on physical computers where you basically run your code, which can help. But before you get to that point, you need to know that the data is actually available, and you need to know how it looks to write program to run your analysis, right? So what we want to get to is eventually ways to make this data more findable, accessible, interoperable, and reusable through metadata-driven discovery and analysis. And I've highlighted the word ability there because we don't want to make this data open, of course, but we want to allow it to have the ability to be found, like people can actually find it and eventually access and use it. The difference between data and metadata, the relationship, I like to see them as an iceberg, that the data is sort of at the bottom of this iceberg, contains all of the cell values, the granularity, if you want, of the data set itself. And the metadata, it's what comes at the top. So it's top level information. I'm not sure how familiar you are with RDF, but I'm gonna briefly talk about that schema specifically there that we use to describe the metadata. But it contains only top level information where we basically remove the singular cell values, and we just describe the data set as a whole without going into the specific. And that's also what we call the counterpart of that. That's what we call the dataless table, which is a table that in a way, we're gonna see how we can retain some of the structural components of the table, but without actually showing any of the data it's signed. The schema that you just saw briefly on how we can describe a metadata comes from this work that we did on ontology engineering, and we looked at how we can build a model or a schema that describes important concept of a table. And specifically, we look at the structure of a table, the statistics of a table, and also the semantics. So what does the table describes? And it can go far beyond this, what's inside the table, but this was a starting point that we thought these are the main components in a way that helps us or define what a tabular data is. And we do this, this process is done, we want to preserve the confidentiality. So we're gonna see how we can do this without having to go and touch the singular cell values. So this is the schema that we came up with. It can be extended, of course, but the main concept is that the purple part, it's the structural layer of the table. So through those concepts and properties, we are able to define how the table looks. We are also able to add information about some summary statistics, very basic. How many columns are there? How many rows? What's the completeness of the table or each column? And we can also add information about what are the values inside in terms of, are the numerical value, are the categorical values? And these are all information that are needed if we have to write a program to then go and analyze this data. We need to know how this data looks, if it's, categories or numbers or and so on. And we're also able to describe the semantic of each column or variable. So what is it measured in this specific column? And we're able to link that to control vocabularies and other properties that we can reuse on the web. Now, this is great, but in practice, how do you do it? You can obviously manually generate your metadata following this, or we've built a very basic Python package to do that, that at the moment only takes CSV files and sort of plain tables, so not like nested funky tables. And this one mostly builds the structural part of your metadata. We're actually looking at ways with the Benno, I'm not sure if some of you might know it, how we can add maybe some automatic way to also add the semantic part based on some of the other work that I'm going to show, and also how to infer whether values are categorical, nominal, and so on. So that's hopefully it's going to come soon, but you're happy to use this in the meantime. Great. So we have our metadata. We want to do stuff with it now. We want to try and do things that people usually do with data, with tabular data in general. And one of the things that we look at is semantic table interpretation, which is a process of annotating the elements of this table, both at the structural and context level, with some meaningful semantic about the table itself. And this is done for schema matching, how we can enhance dataset search and retrieval, data integration, and so on. So we went to look at what are the common things done in semantic table interpretation. And these are some of the tasks, like column type annotation, cell entity annotation. We want to add all of these important semantics to our table so that we can reuse it, we can map them to other things. The problem is that most, if not all of the tools or algorithm proposed, they remove the columns, which is pretty much the only thing that we have, right? So if we remove the cell values, we are left with the structure of the table, we are left with the semantic of the column headers, but what's already available didn't account that. So we couldn't really reuse these things. And we're like, how do we actually add the semantic when we don't have the data itself and all available solutions work only with the data? One option is to, this is just to show that our ontology actually allows for this. One solution is to do manual annotations, but that's very labor intensive, as I'm sure you know. And it's also domain specific, right? We can't just get a random annotators to annotate a table they don't know anything about. So obviously we thought, okay, can we just use large language models to do this?
Yeah. Clarify. So you're not using the underlying data.
Mm-hmm.
You have no schema information, so no headers or anything.
We have headers. That's the only thing we have, pretty much. Yes.
That doesn't sound cool, zero, cool.
Yeah. So those are the usual algorithm or proposed solutions for some of these tasks. And if you go look at most of the benchmarks available or the solution proposed, they just remove the column headers. Or if they're kept in terms of relationship. So how, like maybe the order, how they're ranked. So we had to come up with ways, to be like, okay, how do we actually reuse this? And this was actually difficult even to find data set to use as benchmarks, because most of the data sets outside for benchmarks in this, they show the data, but they remove the columns.
Yeah.
So yeah, it was quite challenging that. So we looked at, okay, can we use LLMs? And we did 2 experiments on this. I'm gonna go briefly through the first one because this was early 2023. We used web interfaces. We didn't even use the API. It was a naive sort of type of approach. But I think what we were trying to do is annotate this column header using, at the time, LLMs. But mostly we were looking at how can we actually evaluate this annotation, because we don't know whether this annotation is correct in a way. We don't have a benchmark for it. So how do we know, how can we evaluate it, right, without having a benchmark? And I think that's what's the most interesting part of this. It's what we propose sort of as evaluation, which in a way is that we look at the internal consistency of the LLM, and this is done a bit different than previous time maybe, but we do it through a pairwise alignment. So we basically align all the possible responses that the LLM gives through multiple iteration, and we basically align them between each other. And the assumption there is that if the LLM is very consistent in the annotation that gives us, we can give a bit more trust into the annotation. We also looked at how we can do this with multiple LLMs. So if we have 2 LLMs, let's say, or even 2 versions of the same model that gives us the same, they are consistent in the same way, that can help us, it's a metric that we can use to evaluate this annotation. And we also looked at human-computer agreement, and this is, we don't have to go through this, but it's slightly different than your annotator agreement in a way. Here, the assumption is that this annotation, even if they're human-made, they might be different because people might have different views on this annotation. So we could consider the annotation right from an LLM if it's the same as at least one of the human. So it's a slightly different ways of looking at agreement. But as I said, we didn't use the API. It was a large context window approach, so it wasn't great if you are using a lot of data and so on. We still find this, the LLM were consistent, but we wanted to go a bit further. And we were lucky enough that the semantic tab challenge, which I'm not sure if you know what it is, but it's part of a challenge at the ISWC conference, came up. And the challenge itself was pretty much based on what we were doing. So the challenge itself was to annotate metadata from tables without the data itself and map it to a control vocabulary. And what we did here is we didn't use a large context window approach. We used a RAG approach for this. But we only also looked at traditional semantic similarity methods to perform this. So far we said, okay, LLMs are great, but a simpler, more traditional method also work with this. Do we have to go all the way to LLMs to perform this, or traditional methods are enough? And we also played a little bit with the temperature of the LLM. This was mostly for curiosity, but we wanted to know whether it makes a difference in some ways. And what we found, this is, well, briefly the methods, but we had 2 different rounds where the data was actually different, where we basically had different metadata, different glossary. We went first into the LLM approach. We used 4 different LLMs. 3 GPT, and then 4 sort of open source, 5 different LLM temperature, and we basically had the prompt with the instruction of the LLM and the glossary, so the annotation we were trying to do were stored in the vector store. So we were basically asking the LLM, this is your metadata, you have the stuff in your vector store, what's the annotation, pretty much. But we also did more a traditional approach with SentenceBird, where basically we embedded the metadata, we embedded the glossary, and then we computed the cosine similarity between the embeddings. And we compared the output, pretty much. What we found, this is the LLM results, is that especially at lower temperature, let's say 1 and lower, 0.75, I think was the best, yeah, the LLMs, especially the GPT models, were doing very good. This is accuracy scores over the ground truth, so they're pretty high, considering, you know, what we were working with. But for round two, instead, they did very, very, very bad. In a lot of cases, either the annotation were completely wrong, or they were hallucinated, they were not in the vocabulary that we were looking at, or they just didn't have, the LLM was just not giving a response. This was mostly on the Llama and Gemma models.
Wait, can you remember what was round two again?
This is round two, and that's round one. So the data is different, and I'm gonna show you why it's different in a second. But the metadata and the glossary are different for these two rounds. And at the time, we were like, okay, but we were expecting the same results. And then we went to look at, okay, what's inside this metadata and glossary, and we realized that there is a big difference in what's in there.
Wait, what is X?
X, it's when you don't get a response. Like the LLM was just not returning anything. 0, it's when you get the response, but it's not it's not the annotation, pretty much. So or either the LLM would be like, I can't do this. And the X is, it was just, Gemma was just not computing. It was just not returning. These are all with the API, actually. They're all connected with the API. But I mean, some of these results are pretty good. You know, this is a very naive approach. There is no really, like, you know, the fine tuning. We didn't give any examples of this in the prompt. So it was very naive, and the results were fairly decent.
How large is your glossary here?
They were different. So this one was larger than this one. This one, I think, was about 1,200 terms. And this one was, I think, maybe 2,000. So as a task, you're asking, okay, given this column header, which is, you know, maybe a word, 2 words, 3 words, find the concept among these 1,200 concepts. So it's fairly decent as a result that we didn't expect, right? But I think what I find even more interesting is the fact that sentence BERT, so traditional semantic similarity approach, also worked great. Round one, not that much, but in round two, they pretty much outperformed the LLMs in terms of accuracy. It's different combination of the metadata that we did for the embedding itself, because also there we wanted to explore a little bit, like, okay, is the LLM, is the embeddings more important if I do it for the label by itself, or for the label and the table name, or, you know, different combinations of this. Again, it was very exploratory. We were playing around a little bit with the settings. So what is the difference between these two rounds? Round one was very, very, very general. This is just an example. This is the metadata that we get from the table. So we have an ID, which we don't really might necessarily need. Maybe there's some information at the back there that we might want to use. We have the table name and the table columns. So this is the column headers of the table. And this metadata was quite a lot. I don't remember now exactly the number, but it was very general, had to be mapped with DBpedia properties. Now, I don't know if you have experience with DBpedia properties, but again, they are very, very general, right? Because they come from DBpedia. They don't necessarily specify something that is very specific or niche. In round two, it was very, very niche instead. And we had stuff about Pokemon and a glossary about Pokemon. We had other things, for example, about the price of a Big Mac in different countries. Mm-hmm. So it was so specific and niche that we think, well, in these cases where what you're trying to annotate and what you're using for annotation are so aligned, possibly some traditional semantic similarity approach actually work better or comparable, right? This was quite interesting to see. So yeah, the summary of this one was, look, yeah, the LLM performed quite well. We can use them, of course, especially at lower temperature, but we can also use traditional semantic similarity approaches. And it's really important in this case is to look at what is being annotated and what we are actually using for this annotation. And this is just to say that I don't think there is one way to make this annotation in the metadata. There are several, and maybe like more traditional one also work as good. Great. Now we have been able to generate our metadata. We have a schema to do so. We can enrich it in some ways. Again, what do we do with this? And what we were trying to do here is something that is called table union search, but only using metadata information. And it's table union search. It's a problem where you have a data lake, and given a query table, you want to find candidate tables that can be unioned to that table. And can we use our metadata for that, pretty much? And how does a metadata approach compare against the state-of-the-art data-driven approach? This is an example of what table union search is. It's defined as the K table that are most likely to be unionable with the given search table. This is an example of two tables that can be unioned. You can see that some of the information might be similar, but the table looks quite different in terms of column headers or how the actual values are displayed. And our approach instead, we call it metadata union search. And we first have to generate and enrich the metadata. We had 4 different versions of this. We had some that it was like basic metadata, and then we enriched it with data types and again, DBpedia properties. We compute again the embeddings of the metadata for all of this table inside the data lakes. We measure the cosine similarities between them. We then calculate a similarity threshold. Why? Because the cosine similarity alone doesn't tell us whether 2 tables are actually unionable or not. So what we did is that we went into the benchmark and we took part of the tables that were that we knew that could be unioned, and we calculated the cosine similarity threshold, for which we said if tables have a cosine similarity threshold above these, then we consider them as unionable. And what we found is that we actually performed better than the state-of-the-art data-driven approaches. And this was against the benchmark. And we did not expect this at all. There could be a lot of reasons why is this. There could be the benchmark is not that good. It's the first one, which it could be, right? But also it's why does this happen, right? If we use a very basic, I mean, not basic, but simpler approach, which we just calculate embeddings of the metadata, we are able to actually beat algorithm that might have to run for I don't even know how many hours or days to compute this unionability, because this table can be huge, when in fact, you know, we can just do it in a few minutes, pretty much. And this was something that we didn't really expect. And it was very interesting to see. These are all of the different versions of the metadata that we had. It was also quite interesting to see that the basic one, so the one without annotation, performed best, which we also didn't expect. But yeah, it was an interesting result. So summary, we have defined what dataless tables are. We've shown how metadata can be used to describe them. We've also explored different ways we can enrich the metadata and how we can do some downstream tasks, such as integration, and how this can be used also for search. Now, beyond the restricted data realm, we can actually apply this to any data ecosystem, right? So Google dataset search, for example, rely on metadata information. So if we could add information about confidential data through the metadata, we can also do it for open data. And how can we then, you know, how much can we actually improve retrieval and all other tasks just adding metadata information? And that's it. Thank you. Are there any questions?
I have one question on your benchmark, just to understand. So how did you edit the benchmark, if I understood correctly, or
Yeah, yeah.
using some similarities or to inform something.
About this, the
Yeah,
benchmark.
about this last project.
So there is a benchmark to do. There are several benchmarks to do table union search.
Yeah.
Only the latest one actually has column headers. So that's when we were able to actually do this, because all the previous one didn't have column headers information. So we couldn't even attempt to try and do this.
Yeah.
And we basically split the benchmark. What the benchmark gives you is sets pairs of tables that are unionable and that are not unionable.
Okay, yeah.
So
Yeah.
we split it. I think we took 20% of it. We basically ran our embeddings. We then calculated the cosine similarities between all of the different pairs of the split. And then we went to check in the benchmark if this specific pair was unionable or not. So if, say, like a pair had a cosine similarity, I don't know, of 0.7, the benchmark told us this pair is unionable. And then we calculated it this over all of the pairs that we had.
The threshold based on
A split.
data in the benchmark.
Yes, yeah.
But these are like all distinctive pairs, right?
Yes,
so
yes.
There's no linkage from your training.
No.
You infer this threshold and.
No, we removed them.
All
yes,
right,
yeah.
Okay.
We split the benchmark to, yeah, we removed them at the end. The test didn't include them. Yes.
I also had a question on this project.
Yeah.
You showed that the results were actually best when you included the least metadata.
Yeah.
I was wondering if you tried out different embedding models.
Yeah, that's a great question. We didn't.
Because we looked into something similar on table retrieval.
Yeah.
Where we actually had, well, I saw that more modern embedding models that are trained on embedding longer text are also more capable of representing more of that context. So yeah, that might be.
Yeah, that's a great point. No, we didn't. We actually used the same embedding model that we used for the previous research that we did. But sure, I mean, I completely agree. We can go much further than this. I mean, and the basic metadata, it's pretty much what we show in the ontology without the annotation. So we still have some structure there, but yeah, probably different embedding models would also perform differently.
All right, I think we need
Yes.
to save the rest of the question for after. But thanks once again.
Thank you.
For